Hello, this is the pre-described recording that we're going to do of the lab practical practice problems. Um, in case you missed the Tuesday office hours kind of live solving, it took about an hour 45. I'm sure people will be watching this video to kind of answer questions about the problems they don't know how to do, but the this video is for me to basically solve these problems from scratch using no base code or whatever, and kind of explain the thought process and the methodologies behind these problems. So we'll start with question one. Question one reads, estimate the value of pi using this multiplicative series. So this is an algorithm that represents an estimation for the value of pi. We're going to use 100,000 of these fractional terms made up of four integers. Three of these terms appear in the equation above. Your script should output your computed estimate for the value of pi. So we have some value of pi divided by 2. So at the end, we're going to remember to multiply by 2 to get the estimate of pi. And it's equal to the product of these three terms. And so what I need to do is I need to make a product of essentially 100,000 terms, multiply them together, and get uh, this pi over 2 estimate. So here at problem 2, I know I need to make 100,000 terms, so I'll just go ahead and write a for loop. Let's say n equals 1 to 100,000. We'll start there. Okay, so if we look at the first term here, 2 times 2 over 1 times 3. So if this is the first term, let's say, just for the sake of argument, n equals 1 for now. This is just something to help us keep track of what's happening. So we need to make the term, let's make the term 2 times 2 divided by 1 times 3, right? So it looks like, we'll just make some term equals equal to. So for n equals 1, our first term should be 2 times 2 and then 1 times 3. For the second term, for n equals 2, we would need to make the term, let's forget the comments, make the term, and that would be 4, 4, 3, 5. 4 times 4 divided by 3 times 5. So for n equals 1, we're going to make this term, and n equals 2 we make this term, 4 times 4, 3 times 5. Hopefully you can understand the pattern. It looks like the top terms, in this case 2, is just 2 times the n term squared. So 2 times the n term squared is 2 times 2. Here it's 4 times 4. The next term would be, if n equals 3, it'd be 6 times 6. So we'll say up top it's 2 times the n term, and we'll square that, and that's divided by, we can be really careful with our parentheses if we want to. Down below, it looks like it's 2 times the n term minus 1 times 2 times the n term minus 3, right? So this number down below is always 1 below this number and 1 above this number. So here's 2 times n. So it's 2 times n minus 1 and 2 times n plus 1. So we can throw that in there. 2 times n plus 1 times 2 times n minus 1. So we have some term there. And we'll organize this with spaces. In MATLAB, spaces don't really matter in arithmetic operations, so we can kind of organize this. Someone in lab class pointed out that this is 2n squared, and this is 2n squared plus or minus 1. So this is the value 4, and this is the value 3. This is the value 16, and this is the value 15. And if you look at the next term, it's 36 divided by 35. So you could also do that pattern, but I think this one's more straightforward. Doesn't really matter which one you do. Okay, so now we have the term. So how do we make a running product? So hopefully, in a few of our labs, we've made something called a running sum. Generally, we'll say something like, running sum is equal to its previous value, running sum plus some value. And sometimes it's 1. This could make something like a counter. In this case, since we don't want, a sum, we want a product, we'll make this a running product. So let's call this a running product. It doesn't matter what its name is, it's just a variable name. But just to keep track of what it is, we have a running product is equal to running product plus 1. So really what we want is we don't want this to add 1 every time. We want this to multiply by our term. So we're going to multiply this term here. And then if that's true, we need to initialize this value. So running product is equal to 1. So generally with running sums, we initialize our variable at 0 because the counter should start at 0. But for the running product, you'll notice that, if we go through the first iteration of this value, this will be, if this were 0, it would be some new value for running product is equal to 0 times term. And so this value will actually never increase. The product of 0 with anything is still 0. If we start at 1, then our first term will be, after n runs once, this will be this new value, running product, is equal to its old value, which is 1 times the term. So then the first new value will be just basically the term times 1, or the term. And that's what we want, right? Our first value is going to be our first term. And then every loop iteration, we just multiply a new term in. So at the end of this, at the very end of all 100,000 loops, we're going to end up with a running product, so we can display that if we want. And so what we can do is we can run this section, and we get 1.57. Recall that we solved this for pi over 2, so we'll just say at the very end, we can just reassign this value to itself and throw a 2 on there. And what we'll get, hopefully, is an estimation for pi. And I suppressed it, so let's unsuppress it. And we get 3.1416, pretty close to 3.14159, whatever x number of pi terms that you need. I couldn't tell you more than that. So yeah, that's a pretty simple first problem. It's basically understanding how to run a for loop to generate terms that you need, and then understanding how to take a running product. Okay, question 2. Click on this link to view a problem regarding apoptosis. Let's change this format. Instead of sectioning them off like this, we're just going to make new scripts every time. The reason for that is because of how this next problem is structured. We'll just do that. Okay. Problem 2 is structured, excuse me, in this way. It's a question inherently about ODE 45. It reads like this. It reads, consider the apoptosis behavior in cells. The system is controlled by a number of compounds according to the reactions that obey the following system of ODEs. And there's 6 of them, unfortunately. At the end, it wants us to plot them. And it wants us to use a time span between t equals 0 and t equals 50 for all y. And these are all our y's. So let's structure how to use ODE 45. So there's a few things that sorry about that. Okay, so we were doing problem 2, a problem about apoptosis. I need to actually, never mind, I'll change my settings later. Okay, so for problem 2, we are doing a problem about differential equations using ODE 45. And it wants us to take our variables and set them as variables into 2 variables, t and y. And so I guess starting a problem like this can be a little daunting because there's a lot of things we have to do. So I'm going to kind of lay out a list of things we should do when solving an ODE 45 problem. One of them would be, let's see, we need to set up a function that outputs differential equations for ODE 45 to use. Set up a line that uses the ODE 45 function. And then finally, we'll plot our results. So technically, I guess this one should be the best starting point. We'll set up a line that uses the ODE 45 function. So the problem told us that we need to store variables in store our data in 2 variables called ty. We'll just go ahead and throw those there. What is going to be outputting this information is the function ODE 45. Here, we need to put a function. And this is step 2, the function that outputs differentials. And if you don't remember, you can type help ODE 45, but I do remember. And that ODE 45 needs the following arguments. We need a t-span and a y-naught, which is a time span in some format, t-naught, t-final. And then y-naught stands for initial conditions on all our differentials. So we'll just have a time span here. You can define it separately up here, which we totally will do. Here, and we'll throw it there. And then finally, our initial condition. So let's just call that IC for now. And we'll set IC equal to some vector that will be defined later. Okay, cool. So we don't want t and y to be output, so we'll tell this function here. Let's call this something. Let's call this like ODE functions. Here we'll anonymize it, kind of, which really what this does is this tells our script that it can use this y immediately back into this ODE function. And this ODE function will also take those as inputs. So generally, if you were trying to be safe with ODE 45, this t and y variable will match the inputs to this function, which will match the outputs of this function. Okay, cool. So we've set up the line that uses the ODE45 function. Pretty simple, hopefully, maybe not. And here we'll define it. So if you're in MATLAB, what is this? I'm using 2018b. If you are in MATLAB 2017b and beyond, I believe, then you can define a function at the bottom of your script rather than externally. And so what that means is when I need to define this ODE function to output differential equations, I can do it down here. Function output equals ODE functions, ty. If you're using MATLAB 2017b and before, or sorry, a and before, then you could not do this. It would give you an error. You can't define a function exterior, like inside of a script, and so this is a script. You'd have to create a new file, and you'd have to, define this function, output, etc., and then this VOD functions, etc. But since we're using 2018b and beyond, we can, 2017b and beyond, we can go ahead and define our function down here. So we'll just make some space for our function. It wants an output here and ODE functions here. ODE45 really prefers its differential equations to be output as a column vector. So here we'll put an output is equal to, and we'll remember that this is a column vector by placing some semicolons here. Semicolons, again, create vectors in the column format in MATLAB, and we'll put an additional semicolon to suppress. Actually, we don't need to suppress its output. Actually, maybe you do. Doesn't really matter. Anyways, so let's talk about what we need to code here. So we need the following differential equations coded into our script. So let's really quickly kind of put these side by side so we can kind of look at them while we code. I'll go ahead and zoom in on that. Okay, so we need the following differential equations. So I'm just going to type them in plain text, or not, I guess in code, and then we'll see how they get output by the differential equation. So really quickly, the first one, minus a3 times y02 times yhif minus a4 times yhif times yp300 minus a7 times yp53 times yhif. That's our first one. We'll suppress that. Let's make this a little smaller. Our next one, dy02 is equal to a02 minus a3 times y02 times yhf plus a4 times yhf times yp300 minus a11 times y02. yp300, sorry, dyp300 is equal to negative a4 times yhf times yp300 minus a5 times yp300 times yp53 plus a8. I'm just going to go quickly back and suppress these. dyp53 is equal to ap53 minus a5 yp300, nope, a5 times yp300 times yp53 minus a9 times yp53. Dy casp is equal to a9 times yp53 plus a12 minus a13 times y casp. Why is there an error here? Produces a value that might be unused. Interesting. We'll see that later. dykp is equal to negative a10 times y casp times ykp plus a11 times y02 minus a14 times ykp. Okay, so all of these have been defined. You'll probably notice that a lot of these values, a3, why not, are not defined yet within our function. So we'll take a moment to define them. Down here, we have AIHF, so AHIF is equal to 1.52. Suppress that. A4 is equal to 0.2, A9 is equal to 0.1, A13 is equal to 0.1, A02 is equal to 1.8, A5 is equal to 1,000th, A10 is equal to 0.7, A14 is equal to 0.05, oops, AS14, A14, AP53 is equal to 0.05, A7, 0.7, and so on. Unfortunately, this is the most boring part of the entire video, so if you are bored, I'm sorry. I wish I could skip this, but for some people it is somewhat helpful, I think, to go through everything. So, okay, A13 is not used. Does A13 ever get used up here? Maybe not. Maybe it's just an extraneous constant. Actually, oh, here in dYcasp. Yeah, this is 13. A13. Cool. See? MATLAB helped us. Okay, finally. Not finally. Okay, so we expect this to be in some output, right? So I'm going to decide an order to put this as the output. So I'm just going to use the order that they gave us. DYHIF, DYO2, etc. So we'll put that as the output. Recall that MATLAB ODE45 wants our differential equations output as a column. So here's DYHIF, DYO2, DYP300, DYP53. Let's organize this to make it not terrible. DYCasp and DYKP. So 1, 2, 3, 4, 5, 6 that represents our different equations. So here in this step we define these numerical values, and then here we represent them as differentials to be output into this line here, ODE functions. The last thing to do here is you'll notice that YHIF will never take a value, and all the Y's, YO2, YP300, and etc. YCasp, all these values. So what happens is the ODE45 solver. This kind of happens, I would say, like stepwise or incrementally. This will come out with, it'll look at our first value in our initial condition. It'll step forward by some differential, according to some algorithm called Runge-Kutta or Runge-Kutta. So I don't know how to pronounce that. Runge-Kutta 45, and it'll output a new step, and then that'll put it in Y. Since we take this Y and put it back in, we can come up with like I would say our next Y step. And that will be used as a current value for the next time step. So let me repeat that because I think it's important. What we're doing is we're using a stepping method to solve a numerical differential equation. So we take our current value, we estimate the slope, and we move to a next value based on that slope. That next value becomes our current value when we reiterate through that idea again. So that next value becomes our initial value, and then we'll take that slope at that point and then step forward again. So our steps are stored in Y. And so the order that we throw them in, HIF, YO2, YP300, P53, CASP, KP, etc., those will come back to us in the form of like next step iterations back in Y. So if I need, for example, YHIF, so we'll notice that YHIF, DYHIF is given first in this order. As it comes back, it'll be stored in the first column of Y. So when I need it, YHIF, I can call it as the first value in Y. Likewise, if we follow this order, YO2, if I ever need YO2, I can bring that out from the second level of Y. YP300 will come out from the third level of Y. YP53 will come out as the fourth level of Y. YCasp is going to be in the fifth level, and YKP will be in the sixth level. This error confuses me. A9, do I have an A9? Yeah, times YP53. Yeah, I'm not sure about this error. I think it'll go away in a sec. Kind of strange. Anyways, so now hopefully all these things will be defined. Nothing is underlined as unused, and nothing is hopefully undefined. So we'll see. Our initial condition. So what's important is this order. YHIF is in the first slot, and YO2 is in the second slot, and so on. This is the order I determined from this line right here. And so if I need an initial condition, I can use that same order again. So this initial condition vector expects the initial conditions on all these differentials down here uh, in the same order. So what is the initial condition on YHIF? The initial condition on YHIF is given here as 1. So we'll just say 1. The next one for O2 is 0, 300 0, P53 is 0, CASP is 0, and KP is 0. So this would be our initial condition vector. Cool. What is Y? It's best to separate output variables with commas. I don't care. Okay, so let's quickly run this and see if it gives us any errors. Awesome. Tons of errors. What'd I say? Undefined function variable DYP53 in line 39. Oh, that's just a minus, not an equals. That's what this error was about. Cool. So we'll run that. Cool. And it gave us some value for Y. We're going to open Y up and see what it looks like. Okay, so Y has this kind of structure. It looks like it's a 237 by 6. Since we were solving 6 differential equations, we definitely expected 6 outputs. So it looks like our outputs are structured in columns, where this would be the numerical answer for YHIF. Our problem wants us to plot it. So if we are going to plot it, let's plot it, over here. So we'll put it in the script part of our script, not in the function definition. We could put it down here, but actually I guess you can't because this whole Y has to be generated. So what we need to do is we want to first plot this entire column, right? So let's plot T versus our first column. So our first column is every row in our first column, correct? So we'll see what that gives us real fast. Hopefully that'll output a plot. Cool. So that outputs this plot here. It looks pretty normal. I don't know what it's exactly supposed to look like. So we'll look at that in a second. Here we can hold on and we can plot everything else. T, Y, 2. So that'll plot the second one. If you don't want to use hold on, because hold on is kind of like a, I don't know, it's kind of a weird, I don't love hold on. What we're actually going to do is we're going to just continue using this plot command. So if you have ordered pairs of vectors, so for example, this T and this Y are the same size, so we could plot them against each other. You can actually just keep going. So I could plot T versus Y2, comma 2. So what this will do is this will plot now the first vector, and on top of that plot, it'll plot the second vector of Y, the second column that we needed. In this case, that represents Y02. And we can just keep going. So we're just going to plot all of these really quickly. Let's leave that space for organization. So paste, 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 paste. And so this will be the third column, the fourth column, the fifth column, and the sixth column. Okay, so that'll plot all the things together. And that should be it. That should be what we're doing. So we'll run that. And it gives us this funky graph. We'll see if this matches the answer that was given. And it looks like it matches pretty well. If I resize them, they can look almost identical. So that weird blue line behavior, this weird red line, green line, yep, these are identical. So this is the solution to problem 2. So things to note, set up a line that uses the ODE45 function, and in that case, that's our line 9. Set up a function that outputs the differential. So I called some function here, ODE functions, and then down below I define it. There's a bunch of constants here that basically all are used to make up this wonderful differential set, and then we output that as a column. That comes back into here, and then we plot our results like that. So hopefully not too bad. We'll set up a problem called practice 3. And we'll say this is problem 3. Cool. Okay, so real quickly, I need to open up my microphone so it doesn't keep turning off because it's not playing any sound. Never save. Okay, so I don't want to cut out abruptly. I think I might have done that in the last problem. Anyways, problem 3. We'll maximize this again, and we'll come back here. So problem 3 was, with 1 million points, problem 3. Generate a sample of 1 million points whose coordinates are described by a pair of numbers, x, y. The coordinates x, y are each random numbers that lie between 0 and 1 and produced by using the rand function on MATLAB. Determine if that point is identified by these coordinates. Determine if the point identified by these coordinates lies inside of a circle with a radius of 1 and a center at 0, 0. You know, some if statement. If it does, remember that point, and after all testing, we should estimate pi as 4. We should remember the number of points that land inside the circle, which are the number of points that satisfy this condition, and we should divide by the total number of points. Okay, so our first job, generate a sample of 1 million points, whose coordinates are described by a pair of numbers x, y. There's multiple ways to do this. I am going to do this, let's see. So what I'm between is generating some value for x and y from rand, and then calculating whether or not that sits inside the point, and then throwing it away. Or I could solve it with a vector. Let's solve it with a vector. That seems more interesting, and maybe it'll elucidate kind of how rand works. So let's just say x vector is equal to rand 1, and then we'll make a million random values. So that's 1, 2, 3, 4, 5, 6, 6 zeros. And we'll also make y vector is equal to rand 1 million. Cool. So if I were to run this really quickly, let's go ahead and clear all our other stuff. If I were to run this really quickly, then you could see x vector and y vector are 1 by 1 million doubles. The double is just like the floating point precision. It's just a number. And you'll notice that I get a million values of just random numbers between 0 and 1. If you want, you could look up the help documentation of rand. But essentially what it does, and we'll scroll up here. Essentially what it does is, oops, it makes a 1 by 1 million matrix of random values between 0 and 1, on the standard uniform distribution, which means that all numbers between 0 and 1 are equally likely, in stark contrast to rand-and, which is normally distributed. Anyways, so now we have these values. So I needed to know what I want is let's see. What I want to know is, do these values fall within this condition, x squared plus y squared less than or equal to 1? So let's say let's just do that, right? So let's take x vector and let's square every value. And so to do that, what I can do is I can do an element y square, just like that. Same thing with y vector. And we'll do an element y square. Finally, we will add them, and so we'll just say sum vector is equal to x vect plus y vect. And we'll space that out for clarity. And so what that does is that generates this, right? We have this expression x squared plus y squared now from random numbers. And so all of these, we could do it. We get sum vect. All of these are some values, right? Some of them are less than 1, and some of them are greater than 1, right? The ones that are less than 1 fall within the plane, or fall within, I guess, the circle, and some of them don't, right? Okay, so it'd be pretty easy to figure out how many there are using a for loop, but I want to know if there's a better way using MATLAB. Huh. I wonder what this will return. I wonder if I have a vector 2, 3, 4, 5, and we'll save then something like A, and I say B is equal to A less than 1. Oh wow, less than 3, less than 4. Oh wow, it works. So if I do a logical here, B is A less than 4, and so I defined A as 2, 3, 4, 5, and I said B is equal to A less than 4. So which of these values in A are less than 4? It's the first two, 2 and 3, not 4 and 5. So what this should return is yes, yes, no, no. And what it does return is 1, 1, 0, 0, which is yes, yes, no, no. So if that's true, then we could use this value that says, so we'll say in circle is equal to sum vect less than 1, less than or equal to 1. And then the number of points that we would have is, if these all come up as 1 if it's in the circle, then it'd be this, the number of points, num points is equal to the sum of in circle. Finally, our pi estimate, given by this formula, is pi estimate is equal to 4 times num points divided by the number of things we did, which is a million. So 1 times 10 to the 6th. So we'll try that. Come on, we get 3.1432. Since our solution is based on random numbers, we're going to get pretty our answer is going to vary a bit, but 3.1415 is a pretty good estimate, 2, 3, pretty good estimate of pi. What's great about this is it's scalable. I can make this number arbitrarily large, and I could still calculate this value. Cool. So that's a vector way to do it. In class, I did a for loop way to do it. So let's. I think that one makes a little bit more sense. We don't have to do vector operations, but I think this one is much faster. It's better, I guess people would say. But I think it's more easily understood if we use the for loop. So if you want, you could do that. So we could set some for loop for I equals 1 to 1 million. That's 100,000. A million. Then we could say, x is equal to some random number, y is equal to random number. If you're unsure about what this does, then you could just set it in the command window. We could try it. An empty input in rand technically comes back with a 1 by 1 random number. So it's just a single random number. And we could keep running that if you want. It'll always output some random number between 0 and 1. So here, if we set x and y equal to some random number, then we say if x squared plus y squared is less than or equal to 1. So we have some if logical condition. So if this happens, then let's remember it. Let's start a counter. So counters are generally running sums, right? So up here we'll say running sum is equal to 0. And then we'll say running sum is equal to running sum plus 1. End. End. Right? Doing this loop, this will run a million times, and then we'll keep iterating running sum every time it happens, every time this condition happens, and the end. At the end of that, the number of points we have is called running sum. So we'll say pi estimate, in this case, is equal to 4 times running sum divided by a million. 1, 2, 2, 3, 4, 5, 6. And so if we run that, we get also a pi estimate, 3.1424. 1, 3, that's not so great. 1, 4, 2, 1, 2, 6, etc. Right? Pseudo-random. Cool. I bet we could up that precision if we wanted. We could throw a 0 in there, a 0 there, or we could, we could scale this if we want. Number of samples equals 1 times 10 to the 7th. Num samples. Num samples. So this will give us ever more increasing accurate estimates of pi. 1419, whatever. Maybe it's not so great. Pseudo random. Anyways, there's 2 ways to do problem 3. Sorry, knocked over a bottle. 2 ways to do problem 3. I think both are equally acceptable. This vectorization one is obviously better than this. It takes far less time, but up to you. Okay. Practice problem 4. Okay. Where are we? Write a script which will take the following inputs and calculate some properties of the signal in the function called snrcalc, which you'll develop for this question. So what they want is for us to copy this. We'll put that there. Let's put our characteristic problem 4 at the top. Okay, so what are we doing in this problem? Oops, I started Discord. We want to view this PDF file describing this function. So we want a function that accepts 3 input variables, t, ECG, and noise, which it looks like in MATLAB will be generated for us, t, noise. In this case, I think our signal is called signal, so whatever. And we'll estimate the following things. The SNR can be calculated using the following formula. So we need this formula. SNR equals, this is the standard deviation of the signal squared divided by the standard deviation of the noise squared. So here we have some SNR we're passing in the signal, and it's called ECG. So what I could do here is I could just rename this to signal, so I can always use the word signal so that these words match. They don't have to match. They never have to match. But here, basically what we're saying is, if I called this banana, then what this is going to do is, because this is in the second in this list of 1, 2, 3 objects or variables, then this will take this value signal, whatever variable this is, and then in this workspace for this function, it'll call banana the variable, whatever data was in signal. Totally fine, but here we're just going to name it signal for ease. Okay, so what do we need to do? We need to calculate the SNR estimation. So est SNR, which is an output of our function, is equal to, what is the standard deviation? Oh, is it STD? It is STD. Okay, for vectors, y equals s returns the standard deviation. Okay, so this is equal to the STD of, what are we looking for? The signal divided by the noise. Signal divided by STD noise. The only caveat is that these objects, oops, these objects must be squared. Cool. That was pretty simple. The next one is the real SNR can be calculated using the average power of the signal and noise values, whereas the power can be calculated using this. Okay, so let's kind of parse what this formula wants us to do. So we have a sigma sum notation. So what it's saying is add up everything in this list after you do these things in this list. And this says square every term. So every term will be squared. Then we're going to add up every term except the last one, n minus 1, and then divide by the total number of things. Okay. So here, let's take our list. We need both, right? So let's take our list, and first we'll square every term. So we'll say signal squared is equal to signal, and we'll do an element y squared. So this will take every term and it'll square it. So what we're left with in signal squared is a vector with every term inside signal squared. It's just multiplied by itself. Finally, we'll take summation. Signal summation is equal to, and then that'll be the sum of signal. But we don't need every value, right? We need every value except for the last one. So that'll be the sum of signal squared. And it's not every value, it's 1 to the n minus 1. So this will take every value. So every value will be 1 to the n, or just the whole vector. But since we're saying 1 to the n minus 1, this will take every value except for the last one. That's what this n minus 1 is doing. And then we'll say the signal power, which is what this kind of represents, is just, this is equal to the signal summation divided by the number of things that was in it. So we'll just say the length of signal. So now we have signal power. We're going to take this, and I'm not going to copy it, I'm going to rewrite it. We'll just say the same thing here. It's equal to noise squared, noise summation is equal to the sum of noise squared, 1 to the n minus 1. And finally, noise power is equal to signal, noise summation divided by the length of noise. Finally, we can output our real SNR. It was equal to, and that said, the power of the signal divided by the power of noise. So that's signal power divided by noise power. Cool. So if we run that, we get 1.52 and 6.36. What were we supposed to get? That's question 4. Here, so what did we get? So 1.44 to 1.54. That's 1.52. That's fine. And then 5.9 to 6.3. 6.3. Awesome. Oh, I guess it's outside the bounds slightly, but that's the estimated. Kind of hard to believe we messed this one up, right? I don't think that's true. The standard deviation squared divided by the other standard deviation squared. I think we're fine on that one. I think it's just we lost some RNG noise rolls. But anyways, that's problem 4. Things to note about problem 4: we defined an external function and then we called it. So SNR calc gets used here. These variables don't necessarily have to be the same as these ones, but that's how they're used. And then we output it as SNR and real SNR. Cool. Okay, Prac 5. Okay, problem 5 is a circuit, I believe. Here's something the output of the following circuit uses the input voltage of this. I'm gonna try my absolute hardest to duplicate this in Paint. So we'll start here. Oh man, this is gonna be not the best. but we're trying our best. We're using an op amp here. Some rules about op amps are the following, if you remember them. Op amp rules: inputs have same voltage, inputs take no current. So what we're going to do is, and forgive what I'm about to do because it's going to be awful, but I'm going to try to draw a little node here. We're going to call this node V, right? That kind of follows the first rule. The inputs have the same voltage. The op amp is going to try its gosh darn hardest to make the two inputs the same voltage. And so we're going to assume that it succeeded in analyzing the circuit. They also take no current. So what we're going to do is we're going to analyze current at this point on this node. We'll call this node 1. And we're going to analyze the current at this point. We'll call that node 2. And so if you look at the current through node 1, and I'm sorry, I'm going to draw this out, and it's going to be awful. If you look at the current through node 1, what is the current that comes in through this? So it's definitely the current that goes through here. And that current can be represented by the following. That's going to be V in minus V over R. I'm going to take a shortcut right now. If you read the problem, you'll notice that all the resistances are actually just straight up the same value. So if that's true, I'm just going to call them all R, right? All these values are the same, so I'll just call them R. So that's the current going in, represented by this blue line. Oh, we'll take a green line and represent the current that comes out. The current that comes out can be represented by, let's do that in black. Again, it's just a resistor, so we can represent that by the difference in voltage, V minus V out, divided by R again. In this case, this is R3, and this one was R2. But since they're the same value of R, we can just do that. Okay, real quickly, we'll do some algebra to fix this. And I'm going to solve for V, capital V. So what I'll hopefully get if you do the algebra is V. We'll move this to the other side. Or sorry, we'll move this over here. And we'll get V is equal to V in plus V out over 2. Hopefully your algebra checks out there. The miracle of digital things, we'll just make ourselves more space. Okay, so now we will do node 2. Okay, node 2. The current through a capacitor will represent this in, what is this, maroon? Okay, the current through this capacitor, which is really the current that flows through into this node, that is, if you recall the equation for the formula, or sorry, the equation for the current through the capacitor, it is C dV dt. So this is going to be C times the derivative of the voltage across the capacitor. In this case, it's V in minus V, right? And that will be equal to, what color have we not used? Orange, or I guess red, orange. Orange is fine. This current coming out, recall that this input here takes no current, so really the input that comes here is the same input that comes out, and that input can be represented again by a resistor. So that's going to be V minus, this is, in the problem statement it says that this is ground. Question 5, the triangular symbol is ground. So that's 0 over, and then that's the resistance, right? While we're here, I'm actually going to take this equation, we'll do purple, here, God, here, and we're going to substitute it here and also here. So we're going to take this V value and substitute it with V in plus V out over 2. So what we get in our next step is C times the derivative, and I'm sorry, again, I'm drawing with a mouse, and honestly, I think I'm doing a pretty good job with just a mouse. But this will be, we're just going to go ahead and rationalize, or not, we're going to make this a fraction real fast. 2Vn over 2, same thing as Vn. The reason I did that is because this term is going to get a little ugly. Vn plus, oops, V out over 2. So um, if this v really is substituting in with this minus sign, so if we want to break that minus sign, really this comes out as a minus as well, right? So this term, hopefully, if you're doing your math right, can be broken into this. So 2vn minus 1vn is 1, so this is vn over 2 minus v out over 2, which really is the same thing as c dvn dt over 2 minus c over 2 d, oh gosh, it's getting worse, v out over dt. Okay, yeah, hopefully that's not the worst thing ever to parse. I know it's Microsoft Paint is not the best application for this, and neither is a mouse. But okay, so we have this term, and this term was equal to this term on the right. We didn't substitute this yet. So over here we'll go to, I guess, like a brown. So that this term is equal to, and this is going to be, so this is just v, right? This is v minus 0, which is v, and v is the same as vn plus v over 2. So this turns out to be vn minus v out over 2r. And so that is equal to the miracle of paint, right? We have this, we have this. So, God, that looks awful, but hopefully you got the point. You have this equation. This is the differential equation we're hopefully going to solve. Let's solve this for v out real quickly. We know we could just take the 2 out of everything, and we'll divide c to the other side. So we'll put the c here, and we'll get rid of it here. So overall, what we're left with is, if you solve this equation for dv out, you get d v out dt is equal to dv in dt minus this term minus v out over rc. So this is the differential equation we're going to be solving. You could solve this with OD45 or Euler's method, which are both, remember, numerical ways to solve differential equations. We're going to use Euler's method because I test on it, and I expect people to know it. I think it's really important. So let's do that. Okay, so this differential equation we're doing, real quickly, dv and dt shows up here, and we want to know what that is. We were told, so here, let's do this. Can I make this always on top? No. We're just gonna remember. We're just gonna write it down real fast. dv out is equal to dv in minus, in parentheses, v in minus v out divided by rc. dv out is equal to dv in minus v out all over divided by rc. Cool. Okay, so we're solving this differential equation. We're going to use Euler's method to solve this differential equation. We need some things. So let's first see what we're doing. Label the graph, whatever. Graph the voltage from period 0 to 0.2 seconds. So end time is equal to 0.2 seconds. And we'll set dt equals something small like 0.001. How did I come up with this value? I just chose it. It's small enough. It looks like this number divided by this number. So the number of steps we're going to do is end time divided by dt. So we're going to do that many. Okay, so Euler's method. Euler's for loop stuff. Define a time. Wow. Define a time. Define a slope formulation. Some differential term. Iterate forward in time. Repeat. Okay. We'll use A is equal to 1 to the number of steps. we'll do a time step. So we'll say t of I plus 1 is equal to I times dt. We're going to set, since we initialized an I plus 1 variable, or sorry, not I, this should be a times dt. Since we initialized that, let's start with a simple starting value for t. We'll just say it starts at 0. Over here, let's see. Let's define a slope formulation. Real fast, if you look at the problem, it tells us that our input voltage is 10 sine times 40 pi t. And you'll notice that we also need its derivative, dv and dt. So if we look at this and you find its derivative, hopefully, so we'll write that in MATLAB real fast. Input is equal to 10 times sine of 40 times pi times t. Hopefully you know its derivative, d input, is equal to, and you know what, let's just call this properly. We'll call that Vn. We'll call this Vn. Hopefully you can calculate this derivative. It's 400 times pi times the cosine of 40. 40 times pi times t. So cool. Okay, so let's use those right now. So real quickly, I just want to say the Vn at I at A is equal to this value. The Vn at A is always equal to the time at A times 40 times pi times 10 of sine. So we'll store that value. And we also want to know its derivative at that point in time. Its derivative is equal to 400 times pi times the cosine of 40 times pi times t at A. So its current derivative is equal to this. And so finally what we need is we need a value for dv out. So dv out at any point in time is dv in minus v in's current value, A, minus v out's current value, and all of that divided by RC. We use R and we use C, so we should throw them up here. R is equal to C is equal to, I believe this is 5,000 ohms, and this is a microfarad. Yeah, microfarad, 1 times 10 to the negative 6. Yep. Okay, so that'll define dv out. And finally, iterate forward in time. So what that step is that's v out of I plus 1. So the next value, v out, is equal to the current value of v out plus its derivative times some time step. Finally, that'll be iterated over time. I keep forgetting that I use the index A instead of I. Okay. I need a first value for V out. V out's initial condition is, I believe it starts at 0. We're going to say it starts at 0. And cool. So we'll see what that does. Undefined variable function RC, or time C. Oh, let's just do some clearing. Okay, so what came out? Let's look at V out, dV out, whatever, V in. Okay, so V out is a 1 by 201, V in is a 1 by 200, and T is that. So let's plot that stuff and see what comes out. So let's first plot T versus V out. That doesn't look great. You know what I'm going to do? I'm going to clear all here and we'll run that. Huh. That does not look great. In fact, it looks pretty wrong. What did we do wrong? 400 times pi times the cosine of this, 10 times this. Did we do this math right? V in minus V out divided by RC. V out is equal to V in minus that. Okay, so Huh, that doesn't look sinusoidal at all. Divided by RC. Interesting. Okay. Hmm. Okay, yeah, let's try to debug this. So let's plot that. Plot T versus V in. So let's see what that looks like on the same plot. I'm actually not going to hold on. What I really want to do is T V in. We'll do that. The only thing about this is that T is one index too long. You'll notice that T is 1 by 201 and V in is 200. So we'll shorten that by 1 to make that work. We'll plot that. So what does that look like? Not great. So what's going on here? R is 5,000. C is 1 microfarad. V in is 10 sine 40 pi times t. Its derivative is 40 times 10, which is 400 times pi times its cosine. dv out is equal to dv in minus v in minus v out over rc. Yeah, it should be right. Divided by r times c. And then v out is equal to its new value plus this. So are these values too small? Maybe your time step is too high? Nope. Huh. All right. Well, I'm going to quickly check this out and then I'll come back with the answer. We'll see that in a sec. Hold on.